Okay, now the quality is bad, but at least it's working. How bad is it? Oh, let me check how bad it looks. Again, it looks good enough. Okay, it's not perfect, but yeah, good enough. Good enough. So the quality is now 0.5 megabit per second. It's pretty bad actually, but still picture is still, so it should be enough. Should be enough, I think. We don't have any videos here, so it's just this code. Yeah, 0.5 megabit should be enough. Yeah, but it's working. Yeah, connection is stable. Okay, nice. Oh, let's go. So I'll continue the same game. We open the problem. We try to solve it from the first try without local testing. It's same as usual. I'll open your chat. Chat. Yep. Oh. Stream is working. Stream is working. Outlook and code forces. Yep. Looks fine. Looks fine. Looks fine. Well, let's go. So today we'll try to solve some more problems without local testing. Regular code tests, usually it's too difficult. Yes, I tried to solve the last one, and I didn't solve the last one. It's just too difficult. Maybe I'll try to do it next time. Usually first problems are pretty simple, but these problems are usually much too complicated for these streams. So I spent like a whole hour to solve these problems, and sometimes I didn't manage to solve it. Let's stick with the plan. Okay, so once again, the purpose of these streams is to show you how to solve simple problems. And just for me, it's to train how to solve problems without local testing. That's what I do in the stream. Now, if you only try to solve the first problems of ARC, then it's better to solve ABC. There's a lot of simple problems here. Yeah, maybe first problems are pretty slightly too obvious. Consider simply repeating the operation below. Find the minimum number of pressure and do so. Operation choose one character and replaces with different character. Okay. Languages doesn't have a power function. I believe it has, but it's in double, so why should I use it if I can just multiply? string as empty. We have two desks. Okay, desk one have vertical stack of n books, and B similarly have m books. Okay, so we have two stacks of books. It takes minutes to read the book from the top and this guy, and minutes to read it from the top. Okay. So the problem you have time. Okay, I'll just save it for future. Choose desk with the book remaining. Read the topmost book of the desk and remove it from the desk. How many books can we read at most by repeating the section? So it takes up to... Oh, that's a nice problem. That's a cool problem about 2 pointers. So if you watch my lecture about 2 pointers method, that's exactly what we do in this problem. So we have these two stacks and value k. And we have these two arrays. Like this, right? And now we read some prefix of the first array and some prefix of the second array. And the sum of these two prefixes must be at most k. At most k, right? How to solve this problem? Pretty simple. So we'll have 2 pointers. First pointer is number of books we read from the first stack, and second is number of books we read from the second stack. But first we'll start. So let's say J is the number of books in the second stack. So first we start from the 0 books. Let's make it long. Yeah. No, let's do it like this. We'll just greedily add books from the second stack. So while j is less than m and s plus b, j is less or equal to k, then please. We read this book and add it to the sum. Just greedily read the books from the second stack. And now we add books from the first stacks one by one and move this pointer. So we how many books can we read at most? So now result is just j. So this is the result, the maximum number of books. Now we read 0 books from the first stack and j books from the second stack. And now we add books from this first stack one by one. So first we add the second book from the stack. So we add this book from the first stack. And now we need to remove books from the second stack until s will be equal. So while j is greater or equal than 0, and s is still greater than k, we will remove books from the second stack. So how to remove books from the second stack? The same way, we'll just let's say j minus minus and remove this book from the sum. So again, we add one book to the first stack and remove some books from the second stack. And if is less or equal to k, then we update our result. I plus 1. So I is the index of the last book we read from the first stack, so index of 1 plus 1. So maybe you can do it easier, but That's good enough. Good enough. So first we start by taking some books from the second stack and no books from the first stack. And then we add books from the first stacks one by one. And each time we add one more book to from the first stack, we remove some books from the second stack to keep this sum less or equal to k. Actually, if it is less, you can just break. We can do it like this. So if it is greater than k, it means we can't make it less than k. We just can break here. Update result here. Just for simplicity. That's all. And I have the whole lecture about two pointers method. It will be set if to have some integer overflow at some point. Not here, not here, not here. Yeah, but that's fine. Nice. Again, another way to solve this is to use binary search. You can make a prefix sums, and for each prefix of the first stack, you make binary search to find optimal prefix in the second stack. Another way to solve this. For a positive integer, say, let's say, be number of positive divisors of a given the positive integer and find. Oh, so we need to multiply k by the number of its positive divisors. $10 million. Okay, let's do it another way. So what this sum is for? This sum is actually what we do. We take these divisors and add this k for each of the divisors. So for each divisor of k, we add k to the result, right? So what I will do, I will iterate all possible divisors, and for each divisors, I will add all multiples of this divisor to the results. Let me show you. So what's going on? So you have this function. This function, what does it give you? So you have this sum for each k multiplied by f of k. So f of k is number of divisors. So for example, if k equals to 2, let's say equals to 4, if k equal to 6, then f of k will equal to so we have 1, 2, 3, and 6. Yeah, it's 4. So we have divisors 1, 2, 3, and 6. What I will do? Again, I have this problem focusing. Sorry. I know every time the focus is broken. I know why. So what I will do, I will iterate over these divisors, and for each divisor, I will add this 6 to the result. So I will iterate over each of these elements, and each of these elements will give plus 6 to the result. What does what so let's pick some divisor now. So let's pick some divisor. For this divisor, we need to find all k's such that k is divisible by this d. So we'll iterate each element. So we get 2, 4, 6, 8, and so on. And for all these elements, this d is a divisor. So for each of these elements, we need to add its value to the result. Yeah. So we need to put plus 2 here, plus 4 here, plus 6 here, plus 8 here, and so on. I will calculate this sum and add this sum to the result. So instead of iteration over this k, I will iterate over this divisor. And for each divisor, I will calculate this sum and add this sum to the result. That's the plan. That's the plan. Let's move it here. So I have this int n. Let's write over d. Now for this divisor, I need to find this sum. To find this sum, what is this sum? The sum is actually d multiplied by this 1 plus 2 plus 3 plus and so on. And this is the sum of the arithmetic progression. So I need to find number of elements in this arithmetic progression and then multiply the sum of this arithmetic progression to d. What is number of elements in the progression? We need to find the last element of this progression. Last element of this progression, input n. Thank you so much. That's the most common problem in these strings. So what is the maximal element in this progression? It will be just n divided by d. So this is the maximal element of this progression. It is the last element, such that if we multiply this element by d, we'll get a number less or equal to n. And now we just so we need to add to the result d multiplied by sum of this progression. And sum of the progression is k multiplied by k plus 1, or this. Maybe we have integer overflow here. No, we don't. Since this is n over d, we'll multiply it by d. The number is not more than n, so we'll multiply it and so on. So we don't have integer overflow here. So just put it. I believe that's the whole solution. Now let's check. So we have this for these 4. Yeah, let's see. For these 4, we need to add for divisor 1. We added 1, 2, 3, and 4. For divisor 2, we added here to 4 and to 2 and to 4. So divisor 1 gives you 1 in every sum. Divisor 2 add you this and this, and divisor 3 adds you this, and divisor 4 adds this. So here I have 2, here I have 2, here I have 3. Looks fine. Okay, so now you look at the problem is pretty simple actually. Again, how to solve problems like this? Usually, when you have this sum, you need to think what is the sum is about. So you look at the sum, and you need to find a way to calculate the sum, just reformulating what you are actually calculating. You need to build find some physical meaning of this sum. So this sum is just you take this number k and add this number of times for each divisor. So for each divisor of k, you add k to the result. And now you think about how you can calculate this sum in different orders. So you just basically you reorder the sums of this sum and just to calculate it easily. That's what I do. So instead of going for each individual element of this sum, I calculate it in this. So I group these elements by this value of divisor. Okay, group this value by the same divisor, and then in each group I calculate this sum using this formula for arithmetic progression. That's all. Count the pairs of length and sequence consisting of integers between 1 and m and p that satisfy the following conditions. So they're not equal for each I. Okay. Not equal to aj and bi not equal to bj for every such that. So all integers in each sequence are different, and the corresponding integers in sequences are also different. That's interesting. That's interesting. So I need to pick up, and I have m numbers to pick. Well, that's combinatorics. It may be solved by some dynamic programming. Let's think. How to make dynamic programming here? Let's give you some. So what's going on? You have some integers a, yeah. So you have this array and some this array. So if you just go from left to right and put these integers into the spots, so you go from left to right here. So you fill this prefix and this prefix, and you need to put something here, put something here. And here you cannot put any integer from this set, and here you can't put any integer from this set. That's easy. Okay, that's easy. First, let's put this integer. For this integer, we can put any integer except this. So, no. Not exactly. Not exactly. So for this integer, let's try to put them one by one. So first, let's put one integer in this array, then put integer in this array. When we put this integer, we can put any integer except these ones. Yeah. So you know the number of different integers you can put in this spot. But for this integer, it's a little bit more complicated. So we cannot put any integer from this set, and also can put this integer. So we'll have like m-1 variance, or m-1 minus 1, or m minus I variance. So if we have I integers here, so we have m minus I integers to put here, and for this position we have m-1 or m-1 minus 1, because we also have this. Interesting. Okay, that's not very big, so we can just iterate for all values. Yeah? Maybe we can subtract bad sequences somehow. Maybe we can collate all sequences and then subtract some bad sequences. What is the bad sequence? Bad sequence is when I have the same integer. So if I have some equal integer, so I have here. Yeah, that should be fine. So how to calculate number of good sequences? Yeah, let's say d of n is the number of good sequences of length n. Yeah. So let's try to solve number of all sequences. So number of all different sequences. Yeah. So number of all different sequences will be n factorial square, right? So I pick some. No. It's. I have m values for n positions. Yeah, so it's. So it's something like m factorial divided by m minus n factorial, right? Yeah. So that's the total number of sequences of different elements of length n. So it's square. Will be m factorial divided by m minus n factorial square. So this is the total. Yeah, square. Yeah. So this is the total number of two good sequences. Not n factorial. So I have m values. I have m values, and I need to put them. So again, if you have one sequence, you have m values to put here, m minus 1 value to put here, m minus 2 values to put here, to m minus n plus 1, right? So you need to make a product of this. So it's m factorial divided by m minus 1 factorial, right? Yeah. This looks fine. So I have m possible values to put here, m minus 1 here, and so on. And now I will subtract all bad sequences. Again, what is bad sequence? Bad sequence is when I have some equal number here. So if I have equal number in position I don't like this. So I have some good sequence here. So here are two good sequences. Yeah. So this sequence is good. And here I have anything. So it must be sum for all positions I need to put something here. So it's di. And multiplied by something here. I need to put something here, so it's multiplied by another. No, I don't like that I might multiply it by some. Or is it fine? Is it fine? I need to multiply this sum. No, it's still fine. So if I put some I values here plus here, so what's number of ways to pick this value? For this value, the number of ways to pick it. So I pick I plus 1 numbers here, so it's m minus n minus 1, and so on. Yeah. So I need to multiply this d of I to m minus n minus 1 to m minus n minus 2 to and so on up to m minus n plus 1, something like this. So I need to for each element of this sum, I need to multiply this by this product. Yeah. So what I will do, I will try to keep this sum pre-calculated. So when I move from left to right and calculate d of n, I will have this sum pre-calculated. And this sum changes very simple way. Yes, so when I change this sum, I simply so when I increase n by 1, I add one element here. So every element of this sum will be multiplied by the next multiple here. Shouldn't it be I instead of n minus n multiplied? Which one? Yeah, minus I. Minus I. Yeah. It looks a little bit too complicated, actually. I think it's good enough. Let's try to implement it exactly like it is in this picture. So we have n and m. Yeah. So first we have value for empty sequence. We have one variant. So now we have empty sequence. We have one variant to generate empty sequence. Now let's refer I from n. I have this n. Let's rename this. Never do it like this. And from 0 to n. I just want to do it the same like it is in the picture. Last multiplier should depend on y of n. No, I think it doesn't depend on I, because we need to multiply this suffix, and this suffix not depend on this I. So for each I, this last multiplier is the same. That's my idea. Let me show you. I'll show you in just a second. Yes, and I will keep this product in another source, so along P. So P is this product. So this is P, and this is S. That's my plan. So first, let's calculate this P. So we add one more element to the sequence too. So P will be P multiplied by M minus N plus 1, right? Yeah. So we recalculated this P. Now let's recalculate this sum. Oh, we actually don't need to. Yes, this sum is sum from the previous step, so we'll keep this sum. Or no? No? No, maybe not. So let me think. Yeah. Let's calculate here. Calculate it here. So we will recalculate the S just by multiplying it. So we add this last multiplier to this sum, and also we need to add one more element to this sum, because we added from the previous step, we added this D to this sum. So this we need to add one more element to this sum multiplied by nothing. So if this X is the last element here, yes, so we need to add this last element of the sum. It will be D from the previous step, multiplied by 1, right? Right. How do you account for choosing x for this step? Ah, we need to choose x. And also it's square here. Oh, and here it's also squared. Yeah. Yes, yes. I forgot we need to choose this x somehow. We need to choose this x and we don't know how to choose this x. It's easy. Let's pick any element. Yes. Let's pick one of m elements and use it here. So first let's pick x, put x here, and now fill everything else. Sounds like a plan. Sounds like a plan. So first we pick x, and then we put this yes, if we pick x, then for this prefix we can use only m-1 values. Not working. It's not working. It's not working. Maybe we missed something. Okay. Let's think. I don't know. It's not time for violence. Need to think. No idea. So we need to make two permutations. In each position they should be different. It looks so promising. Maybe we still can do something with it. Put it back. Let's put it back. No, it actually doesn't look promising. Inclusion, exclusion? But how? Yes, let's try. Let's try. So again, if we have some equal positions, so we have some positions, so this equal to this equal to this equal to this. Yes. Imagine we have k such positions. Let's try to calculate number of ways to put it in k such positions. So how to calculate this? Yeah. So we need to put equal elements here and anything here. So we put equal elements here. So we pick some k elements. And put these elements here. So it's m multiplied by m minus 1 multiplied by and so on by m minus k plus 1. It's just to pick these elements. And then we put these elements into some position. So multiply by number of choose from n to k, right? So we pick these positions and put some elements in these positions. And now we need to put something else in all other positions. So we need to multiply this by a number of ways to put something in all other positions. So it will be m minus k multiplied by m minus k minus 1 and so on to m minus n minus 1 square, right? Yes, and now we can use inclusion-exclusion principle, right? So we'll iterate a number of equal elements. For each number of equal elements, we'll calculate this sum, and then we'll either include it or exclude it. Yeah, that sounds fine. That sounds fine. Let's try this. What if you have k equal to 0? If I have k equal to 0, then here I have here I have empty sum. Empty sum will be equal to 1. Multiply by c of n to 0 equal to 1. And then multiply by this, so it will be just this sum square. So if k equal to 0 is just number of all possible pairs of permutations. No, not permutations like this. Oh, the chat is. So if k equal to 0, then it looks fine. So I just have the number of ways to choose two sequences. Looks fine. Let's try this. Let's try this. Let's just erase all these and so k from 0 to n. Now we simply need to calculate these things. So we need to calculate these factorials actually. No, let's calculate factorials. Why not? Is there a simple way to do it? So we fix the bad positions. We put something in these bad positions. So again, yeah, how we calculate the number of ways to do it? So I want to calculate the number of ways to build two sequences such that they have k common elements, at least k common elements. Yeah, so I want some k common elements be equal. So this is number of ways to choose these positions. Now for these positions, I need to pick some values. So this is number of ways to choose these values. And now I need to fill everything else. So this is the number of ways to fill everything else. I will when k is even, I need to add it. When it's odd, I need to subtract it. Let's see. So I'll do something. So if k equal to if k is even, I need to add this value to result. else I will remove the result. That's the plan. Something like this. Now I need to calculate this S is this sum for given K. Subtract. Yeah. Why? Because it's inclusion-exclusion principle. So how do you calculate something? So I need to calculate number of sequences when all elements are different. So I will calculate total number of all elements, then subtract the number of pairs when I have equal elements in one position, when add pairs when I have equal elements in two positions, then subtract when I have three positions, and so on. That's how exclusion principle works, right? You remove all single elements, then add all pairs, then remove all triples, and so on. That should work. That should work. So I need to recalculate these factorials. Let's like this. So I need to pre-calculate factorials. Fact 0 equal to 1 for inverse factorials. So let's just do it like this. Can I do it just like this? Okay, let's do it. Let's do it in smart way. So smart way to calculate. Let's do it like this. You calculate the last inverse factorial, so it will be max minus 1 will be inverse of factorial max minus 1. And then you go from right to left and calculate the inverse factorials. How to calculate the inverse factorial? You take the next inverse factorial and you need to divide it. So to calculate previous inverse factorial, it's the next inverse factorial. So when you calculate factorial, you need to divide it by I plus 2. But here I am, because inverse factorial, so I need to multiply it by I plus 2 plus 1. Like this. So now I need to calculate inverse value only once. I believe it works without this, but still it's fine. Again, we need to calculate power of, I do it all the times, log A, B, 0 if B and 1. Yeah, there's yeah. I know there is a little bit more magic way to calculate this inverse factorial, but yeah, it's still pretty smart actually. It's not the smartest way, but still fine. Yeah. Now we need to calculate this sum. So this sum is just m factorial divided by m minus k factorial. Now this is just n factorial divided by inverse factorial of n minus k. Maybe well, let's calculate. So what I want to do, let me just write it. Maybe we can get rid of something. Maybe not. Maybe not. So I want to, so this is m factorial divided by m minus k factorial. This is n factorial divided by n minus k factorial divided by k factorial. And this is m minus k factorial divided by m minus n factorial, no? Square. Like this. So now let's see, can we remove something? Actually not. We can remove this m minus k and then this m minus k. Right. Oh. Ah. Well, so we can remove this m minus k and this m minus k. Anything else? No? No. What is the easiest way to multiply that many numbers? Well, Kotlin t-shirts, you can contact them directly. I believe there is a contact in this Kotlin, so we'll check on this. Let's finish this. I cannot stop here. So. Yeah. Looks a little bit too much, maybe. Should be easier. Oh, let's go. Oh. 22 milliseconds. How fast are their computers? Ah, we have less than million, so it's 500,000 elements here. So for half a million, no, okay, that's okay. Fair enough. So there's a pretty small number of operations actually. So we have just linear number of operations, and since n is small. Let's finish this and then we'll talk about Kotlin. Okay. N piles of stones. Pile has n stones. Okay, the cache about to use them to play one pawn game. Starting with Aoki. Oh, so sorry. You cannot read. Oh. Yes. So I just so I submitted this and it works just 22 milliseconds. So it actually doesn't matter if you're doing this in a clever way. You can just call this inverse for every element. Since we have only linear number of operations, everything is pretty fast. Sometimes you need to care about doing everything carefully, but not here, since you have only 500,000 operations. Even if you have some complicated operations like this, if you have just 500,000 of operations, it's very fast. So it's like 100 times smaller than time limit. And piles of stones has the cache. You link the problem. Can you please post the link in the chat? Standard to players to remove one operation. Choose one of pile stones and remove one or more stones from it. Oh. Yeah, thank you. So I don't have this URL here. So just usual name, right? It's just name. Yeah. When two players play, there are two possibilities in this game. The player who moves the first always wins, or the player who always wins, only depending on the initial number of stones in this pile. Yes, that's how name works. In such situation, Takashi, the second player to act, is trying to guarantee his win by moving at least 0 and at most a 1 minus 1 stones from the first pile to the second pile. If this is possible, print the number of stones to move, guarantee his victory. Again, the second player wins when the XOR of all elements is 0, right? That's how NIM works. In NIM game, second player wins if the XOR of all elements is 0. It's like a grindy function of this game. So we need to move some stones from first pile to second pile to make the XOR of all elements equal to 0. The question is it possible or not? Interesting. Well, let's see. Let's think. So what's going on again? So I have, let's keep only the first and second numbers. So I have this A1 and A2. Let's call it A and B for simplicity. So I have this first pile and this second pile. And I have all other piles, and the XOR is X. So I want to subtract something from here and add the same number to here. So that the XOR of these two numbers will equal to X. What? Here? Inverse factorial is actually it's just the inverse value of the factorial. So I need, when you calculate the binomial coefficient, you need to divide by factorial. This back here. So here, this number is m factorial divided by m minus k factorial. So I need to be able to divide by some factorial. In modular arithmetics, I calculate everything modular mode. So when you calculate something in modular arithmetics, instead of dividing by that element, you multiply by inverse value of this element. So here, when instead of dividing by this factorial, I multiply by inverse value of this factorial. This will give me divisor. Let's move back. So I need to subtract something from here, add something to here, to make this XOR equal to X. So let's go from the right. Let's go from right to left. Let's look on the last bit of this element. So if XOR already equals to X, so if I have like 0, 1, and here I have 1, if the XOR of these elements is already equals to X, I just keep this last bit. Yeah. So I just use only these bits and I'm fine. If XOR is not equal to X, if I have 0, 0 here and 1 here, can I do something? If I subtract 1 from here, I have 0, I have 1 here, and I will have 1 here. So I will change both bits. Can I do something? It looks like I just cannot do anything. That's strange. Let's look on the last bit of D. So I have this A. Yeah. This is D. This is B. This is X. So if the last bit of D is 0, then I have this last bit will not change. I subtract 0 from here, add 0 to here. The last bit is not changing. So the last bit of the XOR will be the same. If last bit of D is 1, then I subtract it from here, add it to here, and both these bits will change. So XOR will be the same. So the last bit should be fine, yeah? So the last bit should be, so if last bit is wrong, then it's obviously no answer. But for the previous bit, maybe it's different. Yeah, let's look on the previous bit. Let's look on this bit. For this bit, it's not so. This bit may change. So if I have, for example, 1 here and 1 here. Yes, I have 1, 0 here and 1, 0 here. And I want to have 1 in this position. Yeah, something like this. So if I subtract this 1 from here and add it to here, I will have 0, 1 here and 1, 1 here. So I will have this. So by using this last bit, I actually can change the XOR of the previous bit. Interesting. This is always happening. So, and if I have 1, 0 and say, yeah, if I have 1, 1 and 1, 1, There's 1 0 here and 0 0 here, but here I have one extra. Interesting. So when I need to change this second bit, I actually have to use this last bit, right? Maybe we can do this. Maybe I'm overcomplicating things. Let me see. Let me think. Maybe I'm just overcomplicating things. Can we just iterate for all possible D's? No, right? It's 10 power of 12. It's too much, right? So maybe I can split it in halves. Can I split this D into 2 halves? Like, iterate all possible bits here, all possible bits here. I actually can, right? So if I just split this D into 2 halves, so D is 10 power 12. 10 power 12, it's something like 10 power 3 is 10 bits, so it's like 40 bits. So it's like 40 bits number, yeah? Let's speak about 20 bits here and 20 bits here. So if you iterate over last 20 bits of D, then you subtract this D from A, so you know the last 20 bits of A minus D. And you add these 20 bits to B, so you know this last 20 bits of B plus D. Now you must have 0 in these positions, and you change something in these bits, but you cannot change more than one. So you may have -1 in these bits, and you may have +1 in these bits. And that's all. And now when I have -1 here or +1 here, I will check all combinations, and for each combination I will find the left part, which gives me a result equal to 0. Let me show you what I will try to do. Let me show you what I will try to do. And I can't move all stones, right? So the value should be less than A. Okay. Let's just rename it to something P. So I want value A to be A1, I want value B to be P1, and I want value X to be XOR of all other values. Now I need to iterate all possible values here. Well, let's split it into positions, high and low. So high values will be A shifted down 20, and low values will be A Yeah. So these are high 20 bits, these are low 20 bits. Same for here's. Now we iterate through all possible values here. So d low will be from 0 Now we subtract this. We may have less than 0, right? So we subtract this d from this a, and we add this d to this b. And we must have the same bits. So again, we subtract these low bits from these low bits and add these low bits to these low bits. So we'll know these bits and these bits, and this XOR should be equal to 0. Should be equal to x. This XOR this should equal more brackets 2x. Now, if it is, we will look into these positions. So what happens to these bits? Nothing interesting, actually. I don't like it when I just don't like that I may put all the stones. Let's say if I put more than stones than A, then continue. I can put more than A stones. That's important. Now the highest bits will be A minus DL DH2 will be B plus DL. Now I have these high bits. I'll just remember I can get this pair, so I will say Yeah, I'll just make map for each pair. And for this pair, I will add value DL. I still don't like that I can take all elements here. Let's say if I can, let's take the minimum value from this. Yeah, so if I can get this pair without taking all elements, then it will be better. This code is a mess. Yeah, good enough. And now we find all combinations for these pairs. So we will iterate all possible combinations here. Oh, we don't need this. Let's just put this. So we need to take B first, and B first, second. Now we know these bits, and we will iterate all possible these bits. Doesn't matter. Okay. If make it long. So if this number is too much, if dh moved left to 20 plus dl is, so if number is too big, greater or equal than a, then continue. And now we check that to give us the same thing. So AH minus DH it should be at most AH, right? Yes, we cannot make this number negative. So it's AH minus DH. We don't need to take it modular since it's not overflowing. XOR BH plus DH. So if XOR of these two values equal to XH, it means we have good bits here. So we have good bits here for each combination. We have good bits here for these good bits. We have all bits good. Yes. Something like this. Oh, thanks. I still don't know what to do with these bits. But... so we have this, Let's move it to here just to keep it clean. So again, here we iterate over all possible lower bits and try to make XOR of these values equal to XOR of the other. And for each combination, we look what happens in these higher bits, and for each combination here, we do the same trick. Let's check this example, 3 and 5. So 3 is 1, 1, 1 is 1, 1. It's impossible to move something here. Well, since this bit is always 1. Yeah, makes sense. So this bit is always 1, so we can move. 1, 1, 2 is also bad. Because we can't move this one. Yes, not all to put all this. And we check it here. Well, let's try. Or it will be said. Oh. Oh. It was close. It was so close. So the only case it's not working is the last sample test. So sad. It was very close to win this contest. So this test is not working for some reasons. Watch out for overflows. I think I did. Here I have this int. I don't like it. Can't make it long as well. But it should matter because here I make minus and this is long, so it should be long as well. It was so close. I'm sad. I'm very sad, Panda. Yes, it's obviously not 0. But this is since we lost the contest. I already submitted, and it's already wrong answer. See. No, you can spend some time to find the bug, but no, it's not that interesting. How to print number in binary? Yeah. Maybe we have more than 40 bits. What? No. It said 32? Let's say 40. No, right. It's like, let's make 50. It should be 40, right? We have problem even in these bits. What's going on? I don't get it. So even low bits are bad. What? What? No, maybe it's what we look for. So we need it. We don't need it to be 0. We need it to be. We need it to be x. Yeah. So that's what we get, and that's what we need. Sorry, I'm a little bit tired today. No, it's working. What's the problem again? Don't get it again. So what? Need A minus D. XOR B plus D. XOR X. Yeah. This XOR should be 0. Yes, it is 0. I changed this to. It was working for. What? It is working. What's wrong? Don't get it. I don't get it. I have the first pile and have the second pile. Move some elements from here to here. So I have A minus D, B plus D, and XOR of all other elements. What? What's wrong? Maybe it's another sample. Maybe we have different sequence of samples. Let's try all other samples. So 1, minus 1, minus 1, free. Maybe we should minimize something. Player who moves on finished minimize 0 something before game. Minimum numbers. Oh. We need to minimize the answer. Read the statement carefully. Yeah, I think usually there's not so many ways to get the good results. So usually there are just small number of answers, so I pick some answer and it turns out to be minimal one. But in this case there are many possible answers, so I need to pick one. Not fair. That's not fair. So let's talk about Kotlin t-shirts. Kotlin t-shirts. So what's about Kotlin? How to find the posts about Kotlin? There is no link. So how to request t-shirts? I believe there was a link whom to contact to get a t-shirt. I don't know, I believe there was a list of whom to ask to do. I don't know. That's strange. Maybe we'll contact you later. I don't know. Yeah, okay. Maybe it's just not yet. Okay, let's just wait. So what's this problem? ICPC World Finals 2015. Wow. Obviously, the revolution is a technology for many years, given by tools and rapid computers, but the international smartphones, tablets, players, use with computers. Principles, which were physicals. Problem is think about this. Build simulator of this rectangular screen that fully displays 0 mortal windows. Open new window, the top left corner sensor, close open window. Close the pixel, so stop when you're close. Resize, set dimensions. This, it actually looks scary. And what is the number of? It's most of these commands. So you can just do it using brute force. So there's very small number of commands. So there's a small number of windows open. So you just every time you just make you can just make your command just in almost sense. So still no special data. Aha, sorry. You can see what I'm looking for. Sorry. I'm just looking on the problem you suggested to solve. It's problem from some ICPC contest. Again. So it's ICPC World Finals 2015. Again, the problem looks like this. You have this window manager system, and you open some windows, close some windows, and move these windows. So there are several commands. You can open new window, you can close the window, or you can resize or move the currently open window. That's all. Basically, we need to simulate this operation. So each time you change something, you need to simulate what's going on. So basically, you maintain this set of windows and just simulate these operations. And the problem is pretty simple. Since you have only 200 windows open, you can do it just brute force. So when you need to make some iterate, you can just iterate all open windows, and for each window just check if your windows overlap or not. No, it's interesting problem actually. It's this actually close to some real programming. So that's actually what people need to implement when we implement some window managers. So it's interesting since it's like practical. It's not like a strange game when you need to do something strange. It's just really close to something what's going on in real programming. So but it's not hard. It's just you just implement what's written in this code, and that's all. Oh, second lecture, yes, it's pretty good. I like it also. I'm glad you actually like it. It's not easy to implement. Doesn't look hard. Doesn't look hard. This move command may be a little strange, so you need to find maximal. You need to move to the right. So it's not very hard. Failing system test, and you need to find the bug. The easiest way to find the bug is to write a stress test. I think we actually did. I think we I don't know how to check. we planned to implement the feature that you can actually see some first test cases for each program in educational code forces, but I don't know if we implemented it or not. You need to ask Mike. But if you have wrong answer on some big test, you just need to find the bug in your program. That's easiest way to find the bug of a program is to write a stress test. So just generate your own test and compare your result. For segment tree, it's very simple. You can write a program very easily, which calculates your function in brute force. Just calculate very stupid program which answer the query in brute force, and just compare the results of your program and this program on some random tests, and then you will find the bug test. Contact you after, not contact me. Because you need to contact you. If you have runtime on a big test, usually it's because you have a small array, or you have integer overflow, or something else. Try to generate some big test and run your program on this test and see what's going on. Try to generate the maximal possible test. See what's going on. I believe we just cannot open all the tests because they are too big. So especially these large tests, you cannot just download all these big tests because usually these tests are some megabytes of data each test. So it's not useful to open them. We can open small tests so you can debug your program on small tests, but for big tests it's just not useful. It's better to just test program by yourself. Is it only the first contest? We spend too much time on these problems. Let's do another one. Let's do another one. So we almost win this contest. Have one wrong submission because we didn't read what we need to calculate. That's it. We'll buy a product from any given shop. We usually beats. What? Assuming number of builders, right? So how much change will receive? So it's okay. I don't want to think. So this is. Oh no. Oh no, right. Amount of change. Yeah. So it's. Sorry. So we'll round up, we'll play this. So this is the amount we need to pay. And when we subtract that, right? Let me do it again. So this is the number of bills, right? So it's n divided by 1000 rounded up. So it's the sale of this number. We multiply it by 1000 and get the value, and then we subtract n, right? It's fine, right? It would be very sad to fail the first problem. Okay. Cache participant it's submit group A. The problem has n test cases. For each test case, a given string, which is one of these. Okay. Okay. Like this. Because I don't want to think. I like it. I want to keep it. No specific reason. I feel I feel safe when I have this return 0 here. AC. Is it X? Yeah? Wrong answer. TLE. I know. Problem is, I try to not change things which worked. So this template is working, so I'm not changing it. Maybe that's because I'm not that good in C++. So C++, my philosophy is do not change things which works. So. Okay, I have grid of white and black. Okay. Choose some number of rows and some number of columns. And paid red all squares in the chosen rows and all squares in the chosen columns. Okay, you are given positive integer k. How many choices of rows and columns result in exactly k black squares remaining after this operation? 6. Can I just iterate all possible? Why not? Yes, I can iterate all possible values. Why it's HW? It's okay. It's number of black cells result. Forgot to read. Thank you. 0x less than 1. So, like this. Try all possible variants. It's small, yes. Yes, 2 in power of 12, it's very small, so it's, I will not take care of anything. Let's do it. Let's do it twice. So here are columns. Like this, for example, and then we do the same thing for columns. Now we select some columns, select some rows, and now we iteratively look on all cells. If and CJ and black squares, okay, and it is black, so C. Oh, we have C. Let's rename it. And this cell is black. Black is this. Increase result. If it is K, increase result. Looks fine. 2, 1, 2, 3, 4, 5. Okay. Nice. Quickly after finishing the tutorial, let's set to visit a particular place and players who happen to be there. Some players including you, number and the friend is not. Keyboards like very default keyboard. Friendliness. Arrive place. Some order to make sure nobody gets lost. You have already arrived. Should be from a circle. Player who just arrived, they should be cut into the circle somewhere. So we cut one by one, and each time you put your in a circle some position. When each player accepts the first one to arrive or is placed, the player gets comfort equal to the smaller of the friendliness. Smaller of the friendliness of the clockwise adjacent player and the counterclockwise adjacent player. Huh? Yeah, yes, right. You can solve this problem for big constraint, but since constraints are small, you can solve it in a simple way. You don't need to think. Sometimes it's actually, when you make a problem, it's not always good to have a maximal possible constraint. Sometimes it's nice to have small constraints, just to let contestants do whatever solutions they want to. So, even if a problem can be solved with large constraints, it's not always good to have large constraints. If you can keep constraints small and the problem is still fine, keep constraints small. Gets the comfort of 0. The first one. Okay. What is the maximal total comfort of players can get by optimally choosing the order of arrivals? I can choose the order of arrivals and the positions. Interesting. Have a picture. First, second, comfort is 3. For this, comfort is 2 because it's minimum of these values. But this is 2. Interesting. It looks like you need to add elements by decreasing its value. Can we prove this? Let's prove the last person should have minimal value. The last person should have minimal value. If it doesn't have the last minimal value, and we have some minimal element here. Yes, we can remove this minimal element with this element. We can swap them, and the sum will be not smaller. Yeah, I think it's true. So we need to add elements by removing of this value. By decreasing value, something. Add elements by decreasing of the value of these elements. And now we need to find the optimal order and positions. Okay, so add maximal element. Now we add second to maximal element. It has value this. Okay. Now we add the third element. We always have this. Okay, so we always have situation like this. I believe the optimal way is just to put elements in these positions. So we have maximal element, have second two maximal elements here and here. Maybe not. No, that's wrong. That's wrong. It's bigger. So it must be something very simple. Must be very simple. Let's think. So we have this circle. We add the maximal element. Let's learn from 10 to 1. Yeah. So add 10. Now we add 9. After this 10 will never be the minimal element, because for each element there is another neighbor. So we have 10 for these elements. So we can safely replace this 10 with 9, right? So for each element now, one of the neighboring elements is always less than 10. We can actually mark this as, so this element is not important anymore. It will never be the minimal element. And now we add 8. So answer will be 9. Let's try this. So we put 7 here. The answer will be 9. Yeah. Now we can put something here and here. So it will be 6 and 5. So answer will be 8. So 8 plus 8. Now we can put something here. So it will be 7 and 7. I want to maximize number of times I use the element as the minimal element. So each element may be the minimal element only twice. Yes? Because I have this segment one side and then segment to another side. Yes? So I can only have each element in this final sum at most twice. And using this strategy, I can do it. So for each element, for each max from right to left, I can have it twice in this sum, except a maximal one. So the maximal one will be only once in this sum, and each other element will be twice in this sum. Sounds right? Looks fine. Let's try to implement this. So I have n minus 1 elements in this sequence. Let's add the sort. Let's add sort for it. Let's sort this array. So let's add the first element to this sum, and now we need to add another n minus 2 elements, right? So in this sum we have n minus 1 elements. So we add 1 here and other n minus 2 here. And we need to add element I over 2 plus 1. Right? So add 2 elements. We had element 0, then 1, 1, then 2, 2, then 3, 3, and so on. No? Okay. Whew. So the solution, you see, the solution is pretty simple, but you need to understand what's going on in this problem. So you need to take your problems, try to play with it, just look at what's going on with some small examples and so on. It's a tricky problem, but the solution is pretty simple. When you understand what's going on, the solution is pretty simple. And integers, you will choose exactly k of this integer, find the maximum possible product of the chosen. What? I don't like the program when problem starts like this. Okay, I have n integers. I need to choose k integers with maximal possible product. When you need to maximize the sum of elements, it's pretty simple. But when you work with products, there is a sign, and since you may have negative integers, there will be some problems. Let's see, we take some negative numbers and some positive numbers, right? So we need to take some even number of negative numbers. Sure. So let's put some, so you have your array, right? They have very stupid examples. So you have some negative numbers. Let's say -2, -5, -8, -10, and so on. And you have some positive numbers. Let's say 1, 3, 7, 10 again, and so on. So what you want to do, you want to select some k numbers. So you will select some negative numbers and some positive numbers. If your result is positive, then you want to maximize the absolute value of this result. Okay? So if you can get a positive result, you want to have some maximal possible negative numbers and some maximal possible positive numbers. So you just maximize the modulo or the absolute value of your integer. Yeah? So if you can make right? Yeah. So if your result may be positive, then you simply maximize the absolute value of this result. If your result should be negative, then you minimize the result, the absolute value. That's the whole plan. So what I will do, I will try the maximal possible absolute value. First, let's check if it is possible to make how to check if you can get positive result. Well, let's see. We'll see how it goes. So we have this n and k. Yeah. Now let's put some positive numbers here. We will put zeros. Let's put zeros in positive. It's too complicated. Let's do this. Let's make it easier. So let's put all elements and sort them by the absolute value. Yeah, that's easier. I always forget how to do it. Like this. No? This is the correct way to make sort in this language. I always forgot how to do it. I don't need this when you don't use this. Huh? You don't need this. Just like this. Okay. And I think, yeah. So just sort the element by. Well, let's do it like this. Now let's try to take first to this one's computer sort. Yes, me too. Yes. I have failed to put it easier today just because I cannot read the sorting. It's actually a shame. What model? And now let's remember the sign. What to do with these zeros? Zeros are in the end, so it doesn't matter. Yeah. Oh, they have some. Can I do it like this? No? You don't have sign? No? Maybe. I want to have 0. It doesn't matter actually. I believe it doesn't matter. A greater 0 minus A less 0. Nice. Nice. I like it. Now we have the sigma of this element. So if this sign is 0, it means it will be 0. If it is 1, it's a great rule. So if my number is non-negative, then I just maximize the absolute value. If my number is negative, I need to remove something from this product and add something to this product. So I will iterate all elements from k to n. And try to do something. So what I want to do, if this number is positive, if I have positive number, I want to remove some negative number and add this number instead. Yeah. All right, that's fine. Yes, so I need to remove some number. It must be the minimal possible number with given sign. Okay. Int neg int pos. So I find the minimal negative and minimal positive number, minimal by absolute value. Now, if I have positive number, I will get my sum, remove element, minimal negative element, and multiply it by this element. Okay. So if my current sign is negative, then I can remove this element. I can remove minimal negative element from my set and add this positive element. So my product will be positive, right? Right. So this will be the result. So let's multiply it by I divided by 9. Right. But another way is to multiply by I and divide by minimum positive number. This also will change the sign of our product. So we need to take maximum of these values. Okay. So we'll keep the current maximum. Current maximum will be 0. So now the answer is 0. And now we compare this fraction if I have at least one negative number. I don't like this one as negative. Let's make everything positive. So I need to compare this fraction and this fraction. So how I do it? I just multiply. So I need to calculate AI multiplied by res q greater than res p multiplied by minimum negative. Again, this means that this fraction is better than my current result. Then I just update my current result. Yes, update my current result. Yes. And here I do the same trick, but this also I need to let's put ups everywhere just for simplicity. Greater than the maximum positive. Is the structure compared to programming? Help me get better at the program. No, I don't know anything about it. Usually you just solve the problems that you think are moving you forward. So you need to solve problems which are hard to solve for you now. So you find problems which are hard for you to solve and try to solve these problems. That's the way to go. There's not some special rules how to do it because everybody is different. Okay. Now, if I find something, if it's not 0, I don't want to divide. I want to take my sum and divide it by this. Can I just calculate this sum without one element? I'll just remember the number of elements I want to exclude. I need to find index. I don't like this code. Then I don't like this problem. A2 OG letters, what does it mean? I have no idea. I need to remove negative, and here I need to remove positive. Right. Now I just will calculate the sum of all elements except this one. And then multiply it by res p. Yes. It also would be 0. Okay. No, if it is 0, it's still fine, I think. I also need to change the sign, so I have, so this what? Yeah, make sure. How to see this one? Let's put one more element. I hate this problem. Now, finally, if I cannot make answer positive, I will try it as small as possible. So, I'm having so much fun. You don't say. N minus 1 minus I multiplied, remove this. Okay, let's read it again before submitting. So what we're doing, we take this array, sort the values by decreasing the absolute value of the elements. Now take top k elements from this array, calculate their product modulo, calculate the sign of this product. Now, if the sign is non-negative, it means that we take the maximal possible value, we just normalize it and output it. Okay, now the sign is negative, so we made some product and this product is negative. Let's find the minimal negative and possible numbers in these k selected numbers. So again, we look on this k selected number. If it is negative, we update negative number. It's positive, update positive number. So this ni and pi are the indices of this number because of reasons. Nice. So now, miss. What? No. Now we look on all other numbers. If this number is positive and we have some negative number, then we see if this number is better than our current number, update the result. Actually, we can do it only once. Well, it doesn't matter. Update the result. So xx is the number we need to add to the set. X is the number we need to exclude from the set. Okay, so less than 0, and we have some positive. And we have some positive number. Then we remove this positive number, add this number instead. Have some positive result. The result will be multiplied by this fraction, right? Now, if we find something, then let's update the result. Update the result. So we take sum of all elements except this plus this xxx. Normalize output. If not, it means we cannot make a positive result. So we try to operate it as whatever minimal possible negative result. So we iterate last k elements. They are sorted again. They're sorted by absolute value. So take elements with minimal possible absolute value and take the result. I hate this problem. Okay, at least start from the first try. Final one. Cancelled logarithms. The problem is how to calculate logarithm for negative number. For negative numbers, logarithms are kind of strange. Again, the only problem is the only trouble here is that you may have positive and negative numbers, so you need to deal with negative numbers somehow. Yes, you can calculate for minus number. Just check parity of neighbors. What do you mean check? So you find some product and the parity is wrong. So you need to do something. So you build some product and your product is negative. What to do next? You need to do something. No, that's what we do here. You mean for these checks? For these checks, maybe we can. No, I'm not sure if we can have a. I think we actually may. I think you may have some problems with accuracy when you use doubles here. So that's why I do it in integers, because I want to be sure that everything is exactly possible. So I believe you can make a test when these two fractions are very close, so you have problems with accuracy in doubles. Number of negative seconds, and then you need either biggest or smallest. Yeah, that's also a way to solve it. Yeah, it's you need to compare these products. That's the problem. So you want to compare these products using logarithmic arithmetics. I believe you may have problem with accuracy of doubles, since you may have very close products. So logarithms will be very close numbers, and you can distinguish these two doubles. You can check. Taken in pairs. What do you mean? Well, your solution looks easier than mine. Let's try to. Hop. This looks much easier than mine. Let's see what's going on here. So we read this theory, we sort, just sort. Okay, just sort these integers. Take left, right, sign. If k is odd, then we add the rightmost number. So we add the biggest number to the result and remove. So if k is odd, you always need to take the biggest number in the set. Why? Maybe it's true, I don't see why yet, but it's not obvious. Now it well k. And now every time you take the pair with maximal product. Makes sense. So you pick either these two numbers or these two numbers. What is sign? Sign is the current sign of current product. Okay. Cool. Yeah. Well, that looks tricky, but it's actually cool. So you every time you pick pair, so you can pair of positive numbers or you pick pair of negative numbers. Yeah. And then there's only one negative numbers left, and this product will be negative, and this product will still be positive, so it will be fine. Yes, and here sign is negative only when all numbers are negative, because this is the largest possible number. So if sign is negative, it means that all numbers are negative, and you need to pick odd number of these numbers, so the answer is negative. Yeah. Nice, nice. No, that's a cool solution. Much better than mine. But mine still works. My solution still works. And that's the only thing that matters. We have a tree with n vertices and n-1 edges. Okay, again, we have a tree problem again. Another tree problem. Okay, with which connections for integer L. Define a function. I hate these problems. Set of vertices number represents the number of. I hate these problems so much. Connect components in a subgraph formed only by the vertices set S and the edges whose belong to set. I hate problems like this. I just hate them. The tree is big. Just hate this problem. Okay, let's see. I use a help plugin. I tried not to use any plugins in this contest just because I try to keep my setup as simple as possible. Again, the number of connected components is simply n minus number of edges. Since this is a tree, yeah, this is the tree. So the number of connected components, this f, is the n minus number of edges. What is the edge? Number of edges. You have edge when both ends of this edge are in your subset. Yes, your line is great. Again, I'm trying to. It's not as simple as possible could be, but as simple as it's still comfortable for me. You need to keep balancing. Okay. Okay, so you have this tree. Now, what's going on? You pick. So these are your nodes. You pick some segment of the indices of the nodes, and then so you pick this node. So you pick this node, this node, this node, and say let's say this node. These 4 nodes will give you this subgraph. In this subgraph, what is the number of connected components? It's 4 minus this edge. So number of connected components in tree is number of vertices minus number of edges. So here I have 1, 2, 3, 4 nodes minus 1 edge. So I have 3 connected components, 1, 2, and 3. Now, for each segment, I need to calculate sum for all segments. I need to calculate this function. I need to calculate sum of this function for all edges, or for all segments. So I take this segment, calculate this function. This function is different between number of vertices and number of edges. So first let's calculate this. Let's for each segment calculate the number of vertices. It's simple. If you take all edges from L to R, then the number of vertices here is just L plus 1. So you need to calculate the total number of vertices for all segments. That's simple. Now, you want to calculate number of edges. So for each segment, you want to calculate number of edges. Number of edges is simply number of edges, so that both these ends belong to this segment. How to calculate this? That's interesting. Well, let's start from so you have again. You have array of your nodes, yeah. So this is array of your nodes. You want for each segment calculate the number of edges such that both ends of this edge belong to your segment. So what's going on? Let's look on segments like this. So what's going on? You add more and more nodes to your segment. So for each edge, there is a segment when this edge starts to be included in your set. Yeah. So for each edge, you take on indices of these 2 nodes, take minimum of them. So at some point, so you have this node U and V. So you have U and V here. So starting from this segment, your edge is included in your subgraph. Yeah. So your edge is included in these segments. So basically, this edge make +1 for this suffix. So for all segments with right border here, this segment is included. Now, we can iterate for all segments, calculate this. Now we need to move the left border. So let's move the left border of the segment 1 position to the right. When we move the left border 1 position to the right, then some segments are now not included at all. So let's see, this first node X. So you have this node X. So when you exclude your node X from your set, all edges connected to this node X are now not included in your set. So you need to take all these edges and remove them from the result. What does mean remove from the result? You need to find yeah. So you see X, let's say Y. So you have X, you have Y here. So it was included in these segments, and now you need to remove everything from this. Can I do it without segment trees? I believe I can do it without segment trees. I will just go from left to right. Remember these positions. Yeah. So when I remove this segment, I will just remove these values. I don't need to move. I can just calculate this sum. So I look at this. So for each segment, I know the number of for each edge, I know the number of segments which include this edge. Yeah. So I'll just calculate this sum and just modify this sum. Oh, it looks fine. You'll see. Just. I need, Don't use store edges. Yes, you're right. I actually do not. Yes, I think you're right. Yes, you're right. I don't need store edges. I can just add it to result. So for each edge, I know how many segments contain this edge. Yes. So I need left border to be in any position from 0 to x. So there are x plus 1 positions for left border. And right position must be in any place from y to n. So it's n minus y positions, right? Yeah. Again, this now I only calculated number of edges, and that's not. I want to calculate number of connected components. So that's what I should actually remove from the result. And now let's calculate the positive things. So I need to calculate for each segment. Yeah. So for each node, let's calculate number of segments containing this node. Okay, why not? Why not? It's small. You can do it using formula. Yeah. So this node is included. Do I have? Yes, I have segments of one vertex. This node is included in I plus 1 multiplied by n minus I nodes. Right? Right? So each node is included in this number of segments. So I need to add these to the segments. And now I remove edges. So I take this edge belongs to this number of segments. So I remove it from the set. Yeah, it looks fine. Yes. Nice. I forgot to remove pipe again. I forgot to remove the paper. Whew. Summer henchman we spent. Again, we spent almost an hour. That's too much. Need to do it faster. Okay. This positive note, let's end the stream. We have 3 hours of streaming time. Okay, so see you sometime. Not sure when. Maybe on Saturday. Maybe next week. Whew. Okay, it was fun. Thank you for joining today. See you.